if you aren't available, Jeff, if anyone else can do it or not.
With a password, I can leave the room open so time. But
I mean,
without
you wrote
a
it up
password,
very nicely. It's just, I think it's a bit complicated.
Yeah, well, the stream basically.
Number one is never start on time.
Yeah.
Yeah.
Especially in the planetarium, because if you gotta let somebody in late, you flood the place with light and ruin everyone else's day.
Well, there is an official Michigan time policy that used to exist, so that I think it was mostly to give students time to walk from one class to another. But none of the classes ever started on time. It was always at least 5 minutes, after the actual time. But then they put out this very serious email and alert and sent letters to all of us faculty saying, Michigan time is over. We're not doing this anymore. This was a couple of years ago.
Yeah, I was kind of disappointed to hear that. I'd gotten so used to Michigan time. I mean, it was like that since I was an undergrad. So,
Yeah, it was all, you had 10 minutes. If the professor didn't show up in 10 minutes.
Yeah, it was great.
Walk out. The professor usually showed up with 9 minutes and 50 seconds.
I still remember when Dave Snyder was explaining.
You had a backpack and then you...
When I taught, I always started right on time because I packed in a lot.
Remember years ago, Dave Snyder was explaining that to me. Remember you were saying there was regular time and then student time, and that, I believe you said, was a 10-minute offset.
Yep. You had 10 minutes.
So I split the difference and went with 5.
There we go.
Okay.
Wayne State, they changed from a 55-minute hour for lectures to 50-minute hours. So this very subtly destroyed all the professors, right? Because, you go in there with like your notes and you're ready to go, and then class ends 5 minutes early. And 5 minutes adds up over the course of a semester, right? So everybody had to change, but you think, well, 5 minutes, I can just talk a little faster. But that's like a really bad idea.
Okay. I just
31 people.
Just switched over to the open stream for the meeting, so we can get going pretty much any time, I think.
Yeah, we're getting close. 4 minutes. 32 participants now.
Concurrent viewers 2. Well, that means somebody else is getting it. That's good. Yeah, I think I'm going to have to make a habit of connecting up with an Ethernet cable. There's just too much going on for the wireless to handle it.
I still believe in copper.
Yeah, I play around with a program called Jamulus to play music across the internet, and they say flat out, just like, don't even think about wireless. It's not going to work. And they're right. They're right. Concurrent viewings, good connection. I don't know why I'm getting that. Pause settings.
So can I ask about the origin of the Lowbrow name? I mean, who came up with that idea of being the Lowbrows? Always been curious about that.
I wish I knew that, but
wasn't it Jim Loudon in the 80s?
No, it's because we said, since we were being at a university, we said, well, there's the highbrow people, that have the PhDs, and then there's us.
Oh, okay, that makes sense.
Yep.
It's a great name. I thought it would be spelled brow as in B-R-A-U, but it's B-R-O-W, right?
Right.
Yeah.
right.
Lowbrow. Not lowbrow as beer. Lowbrow.
Right.
It was lowbrow until 2020. It was lowbrow with AU, but now it's just back to lowbrow because we haven't been out to celebrate together in a long time.
Right. I've been
So,
asking them since.
We did
It
have a
will
second
change
name.
back once we're safe. It will change back.
We did have our second name, which kind of tells you what beer was around at the time, since we didn't have microbreweries. We were the
Lowenbrow.
Yeah.
Our last guest speaker was Dr. Jessie Christensen from Caltech, and she's from Australia. And she really enjoyed the Kalamazoo name because everyone always gave her grief about the weird names they have in Australia. And so, as a gift for giving a presentation at our last meeting, I sent her a "Yes, there really is a Kalamazoo" T-shirt, and she really enjoyed that.
Oh, that's awesome. Okay. Do you get more speakers from far and wide now that you're doing it on Zoom?
Yeah, I figured why not kind of, quote, take advantage of the situation and try to get speakers you could otherwise never get or would cost you a fortune to fly in, because we've certainly done that. And so I figured, why invite someone from U of M or MSU? We have them come all the time. Why not try to branch out further and, get more variety of speakers? This worked out pretty well. For that last meeting with Dr. Christensen, we had 90 plus in Zoom, and then like another 20 on YouTube. So it was huge. That was our biggest meeting yet.
So I don't think we've ever hit 90.
No, I don't think so either.
We've done 70, but I don't think we've ever done 80. But now we did 90. We have another good speaker for the March meeting too. Guy from SETI talking about how life is probably really rare in the universe, not sort of thing. For the March meeting too. Guy from SETI talking about
I guess YouTube working.
Are you ready to go, Jeff?
Yeah, I think I just checked the YouTube stream and it seems to be working. So,
okay.
Did you?
Right.
Was that what you were seeing, Adrian?
35.
That's exactly what I was saying. The YouTube. I heard the YouTube feed from your main feed, so I figured you were testing it.
Well, my console is looking awfully shaky, but I just checked the URL and it's broadcasting, so I think we're good to go.
Yeah, and let's go for it. So with that, welcome everybody. You have once again found yourself into the Zoom session for the University Lowbrow Astronomers February meeting. As usual, and just as a reminder, we are also recording on YouTube as we do this, just so everybody knows. And as we usually do, we have our guest speakers speak first, because it's possible some people really were just interested in that and didn't want to stick around for our highly entertaining business meeting afterwards. So with that, I am going to move right into introducing our guest speaker tonight. If I just remember to pull this up here. And that is Dr. Sean Gavin, who is a professor at Wayne State University and also an associate chair of physics and astronomy. His main research area is theoretical nuclear physics, especially quark-gluon plasma, high-energy nuclear collisions, and quantum chromodynamics. Sean earned his Bachelor of Science from the State University of New York at Stony Brook and his Master's and PhD from the University of Illinois. He has taught courses in theoretical physics, quantum physics, statistical mechanics, and electromagnetic theory. Currently, he is teaching Physics 7070, Survey of Nuclear Physics. Sean has many publications and won numerous awards from Wayne State, Vanderbilt University, the National Science Foundation, Wayne County, and even the White House, as well as others. Sometimes I like to check out our guest speakers on Rate My Professor. In this case, there are many comments about Sean really knowing his stuff and being very enthusiastic about it. It sounds like he may give hard tests, but grades fairly. Almost all the comments state he is a nice guy, very helpful when asked, and something very important when dealing with our astronomy club, a great sense of humor. So tonight, Sean is with us for a presentation titled Delusion, Fusion, in the Age of the Sun, how a collision between Darwin and Lord Kelvin, sort of, gave rise to modern cosmology. So with that, Sean, you have the floor.
Well, thank you. Thanks for the nice introduction. So welcome to my dining room. Everybody else got the office. My wife and my daughter got the offices with the books. And so all we have here is, I put some Legos there to indicate that I'm a nerd. But so what I will do now is share my monitor, and let's see. So now I'll do the slideshow.
We're seeing it good.
Okay, good. So you've all heard of science denier, heard of people making arguments to suit some idea that they just want to push very recently. But no, it's been going around since forever. And so here's an ancient example, or not so ancient, in which Darwin faced off against Lord Kelvin and sort of gave rise to modern. So let's see. So everybody knows Charles Darwin. He was born in England in 1809. He demonstrated an early interest in natural history. He took a famous voyage on the Beagle, in which he saw lots of sights throughout the world that led him to his idea of natural selection and the theory of evolution. And here on the side, we see, you can see my pointer. Do you see it? Or I don't know if you see it, but there's this picture here shows the evolution of Darwin himself. You can see it started with hair on the top and then slowly migrated downwards. Okay. And so, I should talk, right? But yes, it's there's a lot of beards for a while in this talk, so I have to prepare you for that. Now, evolution is the guiding principle, is one of the big guiding principles in biology. I should mention I'm not a biologist, right? So I'm not a historian, I'm not a biologist. I'm a physicist, but most of the stuff that I'm talking about is not in my area of expertise. So I'm just trying to make a story that sounds interesting and leads you through the ideas that these guys worked with, okay, these people. And so evolution is one of the key driving principles in biology. It's the idea that similar species probably descended from a common ancestor that may be even extinct through a gradual process. And Darwin's mechanism for this was natural selection. And so here's a picture of the famous Darwin finches. They all come from different parts of the Galapagos Islands, and they have different sized beaks because they eat different stuff, and they've been isolated from each other through their reproduction. Now, something that they realized even back in the day was that evolution, if it takes place, must take a very long time. And nowadays we have experiments that clearly demonstrate how evolution works. For example, if you separate fruit flies into two groups and feed them different things, they'll eventually, after several generations, form different breeding populations that can no longer breed with each other. Okay, and so it doesn't just work with fruit flies; it works with people too, and people can trace the evolution of lactose tolerance. It's the ability to drink milk and digest it. How it developed in the European population. It took about 20,000 years, but it's good that this happened because people could create milk on farms and eat all year long with it. Okay. Now, the fossil record implies that large changes probably, and so what is the fossil record? So geologists realized back in Darwin's time that the Earth had to be very old, and they were beginning to dig up the first dinosaurs when Darwin was, a kid. And they found in England the Megalosaurus, the Iguanodon in 1824. This is a picture here of an Iguanodon. It's very different from the sheep that populate England in Darwin's time. So they knew there had to be something that really happened. It had to have been a really long time ago. And in fact, they thought it was so long ago that it may be that the Earth was eternal. And they came up with this idea of uniformitarianism. Uniformitarianism. It's hard to pronounce. But anyway, the idea is that natural processes in the past operate the same as they do now. This came about because of Charles Lyell, who's was Darwin's buddy, his mentor and professor, and he wrote a famous book on principles in geology, in which he proposed that there could be a steady state of volcanism, sedimentation, and erosion that cause features of the Earth to change, but it keeps changing. But it just started a long time. It started infinitely long ago, and it just keeps changing. So when Darwin proposed his idea of evolution, he said, well, how can I show that there's enough time for evolution to take place? So he made a quantitative estimate to support his idea to support the idea of uniformitarianism and evolution. And in The Origin of the Species, he estimated that the erosion of the Weald region in England, and here's England, London is up there, and here's the Weald. And the Weald is sort of carved out of the rock. It was supposed to be a hill that contains folding over layers, but these are all eroded away. So he estimated that it would take 300 million years to erode all that stuff. Now, here's the thing that you need to know about Darwin. He's bad in math, and he made a mistake. He was off by a factor of 10. Modern estimates are more like 30 million years. But in fact, Darwin caught a little flack because he was off by so much. But speaking of which, we get to the meat of our story. While Darwin was saying what basically all of the geologists of the time were saying, that the Earth was very old and that there was enough time for evolution to take place, he was challenged by Lord Kelvin. Lord Kelvin placed limits on the age of the sun and the age of the Earth that contradicted Darwin's estimates. Okay. And so who's Lord Kelvin? Lord Kelvin was born William Thompson. That's his real name. I like to say Lord Kelvin because it sounds like he's a Star Wars character. Okay. But anyway, he was also a brilliant young guy. He published 12 papers by the time he was 16. He became the chair of natural philosophy at the University of Glasgow at age 22. He famously developed the Kelvin scale of absolute temperature in 1848. That's how you've heard of him. But he was knighted for supervising and innovating the construction of the first transatlantic telegraph cable, which is a real technological feat of the day. And later he was named the first Baron Kelvin. Kelvin was the name of the river that flew next to his university in Scotland. And he was given this in part for his invention of the second law of thermodynamics, but also because he was a steadfast opponent of home rule in Northern Ireland. Now to give you an idea of how highly regarded Kelvin was, when he died in 1907, he was buried in Westminster Abbey alongside Sir Isaac Newton. Sir Isaac Newton, he's a big deal, this guy, okay? So, what did he do? He was, primarily, his day job was he's a mathematical physicist. He invented and proved Stokes' theorem. That's funny, right? Because it's named after Stokes. But what happened was he proved the theorem, and he wrote a letter about it. He wrote in a letter to Stokes about this great theorem. And Stokes put it on an exam that was very widely known. And so it became named for Stokes. But that's the way it goes sometimes. He was also a great innovator in the early theory of electromagnetism. He invented what they called the potential. The potential, you'd have heard of things measured in volts, right? That's Kelvin's business, right? And so the other thing he did was he invented a lot of things in the early science of fluid mechanics, when fluid mechanics was being developed. And but really his fame in England, his high regard, came from his work on the transatlantic cable. He was like an Elon Musk of the day. He was the image for people in England of the Industrial Revolution. He helped create the first transatlantic telegraph cable, which is a difficult technological feat because you're sending a wire through a bunch of salt water. And salt dissolved in water, that's a bunch of ions, right? And that really reduces the strength of the signal as it goes across the ocean. So he had to figure out ways to measure the teeny tiny signal that you get on the other side of the Atlantic and pick up the dots and dashes of the telegraph. So all of these inventions led him wealth and fame and knighthood, and he was having a glorious career. But what we remember him for today, what physicists remember him for, is thermodynamics. And he's the first law. He had a lot to do with the first law. This is not so widely known, but he did. First law was developed by Clausius and Rankine, and the first law of thermodynamics, they express the idea that energy is conserved, energy in all of its form. Heat energy, kinetic energy, potential energy, all these different forms of energy can be transformed into one another. He was friends with the famous Joule, the guy who did the experimental determination, the experimental demonstration of the equivalence of work and heat. And he said, Joule said, Kelvin, what's going on with my experiment? And Kelvin said, it's just conservation of energy. He has the unit of energy named after him. But the second law is what he's really known for. In second law, he realized that some of the heat in processes involving steam engines and things like that must be expelled as waste. So you don't. So when you do things involving gases and fluids to create energy, as everybody was learning how to do at that time, you're always going to lose a little bit, and that's really a very important property for today's theme. Okay, but before I mention that, I have to mention that Kelvin, Kelvin was famous throughout the world, and the way we knew about it, the way you can tell is that in Detroit, Michigan, there's a company called Kelvinator that made the first refrigerators. So, how lovely our Kelvinator has kept our salad. It's really, I don't know if anybody still has one of these, but probably in your basement if it's still running. But anyways, so Kelvin applied this, the second law of thermodynamics, and he realized that the sun and the earth have to have finite lifetimes. Okay, so according to him, there could be no perpetual motion. So what that means is that the sun could not be eternal, and that the earth could not be eternal, and even that the universe could not be eternal. Eventually, there would be some heat death in the distant future, in which all of the energy is equally distributed throughout the cosmos. And so Kelvin asked, for the first time using science, okay, how long could all of these things live? How long could the sun and the earth live? And so he said, well, what could produce the sun's heat? And he thought of a few possibilities. He thought, first the sun could burn a fuel, and that fuel would eventually run out, like the gas in the tank of a car. Or it could be continuously supplied with energy from an external force, like if it was plugged into the wall with a power cord. Or the energy could come from gravitational contraction. Turns out that the third possibility is the one that he settled upon. Okay, he dismissed the first possibility because he didn't know of a fuel that could last long enough and provide enough energy to produce the brightness of the sun. Okay, and so his first possibility was, is the sun on fire? So he thought of chemical reactions as providing the source of energy of the sun. And he said, well, maybe the sun is made out of coal, and the coal is burning. Today, we know the sun is made out of hydrogen, so maybe you would guess maybe the hydrogen is burning. And, that hydrogen burns is famously known from the crash of the Hindenburg Zeppelin. The Hindenburg was made out of fire, and the humanity. Anyway, so there's one equation in this talk. Sorry, I have to apologize. There's one equation in this talk. And in this equation, what we do is we take the total energy that's available in the sun, and we divide it by the observed emission rate. So you can measure how bright the sun is, and from the brightness, you can deduce how much energy is coming out of the sun per second. And then you can say how much energy is available. If the sun is made out of coal and it's burning, how much energy is released by the mass of the sun, but made out of coal. And from this, he estimated a lifetime of 10,000 years. And it turns out that that's about the same lifetime that you would get if you had hydrogen. Hydrogen is a much better fuel source than coal. But Lord Kelvin didn't know about all of the invisible forms of electromagnetic radiation, like ultraviolet light and X-rays and radio waves that come from the sun. So if you take those two mistakes and average them out, you end up getting roughly the same amount. So the bottom line is that the sun can't be old enough if the sun can't have been providing energy for this long, if it was burning. Okay. So is there a continuous source of energy? That's a possibility that Kelvin really liked. And he spent a long time thinking that this was probably true. Said, could there be, for example, a constant rain of meteors falling on the sun? And then each time the sun, these meteors fall down, it provides the kinetic energy of the falling meteor is converted into heat as it crashes into the surface of the sun. And so this could have been a possibility for the source of energy in the sun. And Kelvin liked it because it had to do with thermodynamics, which was his expertise. The problem is that it disagreed eventually with experiments. People made measurements. Everybody in the Lowbrow Club probably knows better than I that people made very precise measurements of the rotational period of Mercury around the sun. And then from those measurements, you can deduce that not enough meteorites are there, not enough meteors are there in order to provide the steady flow of energy that would be necessary to produce the heat of the sun. So he thought, well, that's a good idea, but it's wrong. And he moved on, and he started to think, well, maybe gravity could be what's supplying the heat of the sun. And the idea here is that if you think of the sun as being a big blob of gaseous hydrogen, as it burns from the core, it would produce heat, and this heat would be radiated away from the surface layers of the sun. As the heat is radiated away from the surface layers of the sun, the atoms in the surface layer lose kinetic energy. And so they fall down a little bit more. This lowering of the thermal energy means that the matter starts squeezing now more on the core. And so as it squeezes on the core, this makes the core burn hotter. And that keeps the process burning as it falls down, as it slowly crushes down. And eventually, it'll radiate away all of the energy of that heat and then collapse into a dark blob, according to Kelvin. Okay. And so how much energy is there? The total gravitational energy is given by Newton's universal law of gravitation. They know what the mass of the sun is. They know what the size of the sun is, or they had figured it out. Astronomers in the day had figured it out. And from there, you know how much energy there is in the sun. And so from there, you know what the amount of energy there is for gravitational collapse. You know how long how much light is being radiated from the sun per second. And from that, dividing that, you get 20 million years. Okay? And that's the lifetime of the sun, according to Kelvin. Maybe if you fiddle around with the numbers, you get a number that's 200 million years. But Kelvin says this is the maximum age that the sun could have based on the physics that Kelvin knew at the time he wrote this paper in 1850. Okay. So Kelvin said, look, the sun at most is 20 million years old. Darwin says the Earth is 300 million years old. So he who are you going to believe, me or your own eyes? That's Kelvin, and so he said that the geologists basically had to be wrong in thinking that the Earth was infinitely old, and even to think it was as old as they thought it was, he said was wrong. But and so you may think that this is just an isolated scientific thing. A scientist writes a paper and maybe he doesn't even know about Darwin. But in fact, in the paper, if you look at his paper and you read what he wrote, he said, well, what are we to think of such geological estimates as Darwin's estimate of the age of the Weald? Darwin's got to be wrong. Basically, that's what that paragraph says. And so what was Kelvin's motivation for saying this? Well, we can only, but, we don't really have to guess because he wrote about it and talked about it. From the intro to his On the Age of the Sun's Heat paper, said that the second law of thermodynamics says that motion is irreversible. The sun and the earth are therefore not eternal, and the heat death of the universe is even inevitable. Kelvin says it's impossible to conceive either a beginning or a continuance of life without an overruling creative power. So in other words, what Kelvin is saying is that the sun's end requires a beginning, and that this beginning had to require God. Okay? And so let's talk about what Kelvin was missing. Okay? And every kid knows now that the real source of power in the sun is fusion of hydrogen, the nuclei of hydrogen. And the idea of the atom had been coming about sort of in parallel with the lives of Darwin and Kelvin, William Thomson. And so Dalton hypothesized atoms in 1803 in order to explain chemical reactions. Becquerel discovered radioactivity, which came from the nuclear reactions within the reactions of nuclei, not chemical reactions. Thomson in 1897 discovered electrons. Einstein in 1905 discovered the equivalence of mass and energy, where the fantastic energies that come from nuclear reactions are released. And Rutherford in 1911 discovered the atomic nucleus, and he found it to be composed of protons, and later neutrons were discovered in 1932. So there's all this stuff that came about, and it came about really, most of it after Kelvin started arguing with Darwin. Okay? So one of the things here, though, to note, something I'd like to, is that the there's a steady state of evolution towards beardlessness, okay, that's taking place in science and in life in that time. And then you have the idea that fusion powers the sun. This came about in the 1920s, and the idea was that in 1890 they discovered that there was helium in the sun. This contradicted Kelvin's notion that the sun was made out of the same stuff that the Earth is made out of. Okay. And whoops, back. And in 1920, Eddington realized that the fusion of hydrogen into helium can release energy using this equation E equals mc squared from Einstein. And then in 1925, Cecilia Payne-Gaposchkin, studying the the chemical composition of the atmosphere of the sun, realized that the sun is 75% of hydrogen, 24% of helium, and in 1938, Hans Bethe, using the new theory of quantum mechanics, figured out that fusion could take place, and came up with the theory of how fusion could take place. And this is now, without a doubt, what we all know is going on in the sun. Now, in fusion, you get 1,000 times the energy that could possibly be released from gravitational contraction. It's 7 times 10 to the 7th times the energy that's released from chemical burning. And so if you plug this into Kelvin's equation right here, you take the total energy that's available, now assuming the amount of energy that's available in hydrogen fusion, and you estimate and you divide that by the observed luminosity of the sun, you get an age of 10 billion years, okay? And this is compatible now with our modern ideas of what the age of the sun and the earth are. And this was Kelvin's equation, right? But he just didn't know the science. He didn't know at the time that fusion was possible, that nuclear reactions were even possible, okay? So what do we know now about the age of the sun? Fusion powers the low mass. Fusion involves low mass nuclei, which when combined, really, form lighter elements, and these release energy. Helium has slightly less mass than 4 hydrogen nuclei. So when you fuse them together, E equals mc squared from Einstein says that you you can release enough energy to power the sun. It's a much more efficient fuel, but Kelvin couldn't have known this, right? So Kelvin's idea of trying to estimate the age of the sun was a good idea. It was just, he didn't know enough to get the answer right. But Kelvin's idea of energy coming from gravitational collapse is in fact a valid idea. And this is what causes the ignition of stars, we think, in the cosmos. The idea is that Kelvin's mechanism takes place when matter is coalescing from the interstellar medium. The matter rains down and collects, forms heavier and heavier blobs of stuff. As the stuff falls down, it heats up the matter, and eventually the matter gets hotter and hotter. Eventually, it gets hot enough, if there's enough matter around, to ignite fusion, and fusion then burns within the star and keeps the star burning for, maybe billions of years, could be billions of years for a star like ours. Now, this is all good, okay? Where things get a bit rocky, so to speak, is when Kelvin tries to estimate the age of the Earth, okay? Now, his idea here starts out okay. The Earth is formed from the Earth. His idea was that the Earth is composed of rock that could be near the melting temperature of rock. So the Earth is basically solid. So his idea of the structure of the Earth is basically like Jules Verne, from Journey to the Center of the Earth, that basically it's just like a big rock. You could have caves that go down to the center of the Earth, okay? And he thought that, well, if I go and I measure how much heat there is coming out of the Earth, I can go down into mines. He sends his friends down into mines, and they measure the temperature going deeper and deeper into the mines, and he finds that indeed inside the Earth, it's hotter. And so from there, he gets an idea of how much the temperature is dropping through the outside of the Earth. And he says, well, if the Earth is just made out of one big rock, using the laws of heat transfer and thermodynamics. He calculates the age of the Earth, and he gets it to be around 20 to 400 million years old. Okay, now this is the point I can tell you as a theoretical physicist. Okay, this is the point where the lights go off in your mind, and you become totally hooked on a wrong idea. Okay, he has one estimate, which is the age of the sun, and he has another estimate, which is the age of the Earth. Both are wrong, but they get the same answer. So he's like, bingo, I'm right. I have two completely different estimates. They both give me the same answer. I have got to be right. The age of the Earth cannot be more than 400 million years. So he goes around literally speaking to geological conventions, browbeating geologists. And the geologists are like, well, I don't know, maybe he's right. He's this famous guy, right? He's this enormously famous guy, and he's telling us all that we're wrong. Maybe he's right. Okay? Well, as time goes on, eventually people realize, no, I don't know. This is not right. Eventually, Kelvin's former student, John Perry, came to him with an idea where he realized that the inside of the Earth can remain hot for much, much longer if it's made out of molten rock instead of solid rock. And the idea here is that the Earth, instead of being like just a piece of solid stuff that's cooling from the outside in, it's like a styrofoam cup where the crust is the styrofoam and inside is this hot coffee. And in order to make the temperature of the Earth go down, instead of having the temperature be released layer by layer from the outside in, it would have to release all of the heat inside this hot, convecting cup of coffee with all this motion. Now, okay, the inside of the Earth is not liquid in any sense that we understand it, but it's fluid in the sense that you still get this convection, this transport of heat, and of the kind that Perry said would make the temperature inside the whole Earth be far more homogeneous than Kelvin would have expected. Okay, so with this, and again, some math, Perry was able to show that the Earth could easily be billions of years old. And that's without radioactivity. Now, they also knew at the same time, that there was radioactivity. Radioactivity could be a possible source of further heat within the Earth. And from current measurements of neutrinos coming from the inside of the Earth, give you an estimate that maybe 50% of the heat of the Earth comes from radioactive processes within the core, and the other percent, the remaining part, comes from this trapped heat and that Perry was talking about. Okay, so the problem was that Kelvin didn't listen to the geologists. He didn't listen even to his own former student, Perry. By the way, Perry invented, I think, the first electric car. He was an inventor like Kelvin, and people were jacks of all trades back in those days. And so he was only like an incidental geologist. I mean, I think people talked him into going after Lord Kelvin because they figured he's the student of the great man. He's the one Kelvin has to listen to. So he went. So anyway, Kelvin didn't listen to Perry. Kelvin didn't listen to the people like Marie Curie that were discovering radioactivity. He just kind of kept on stomping his feet. And so what happened was there were 50 years of argument over the age of the Earth and the Sun. There was a proxy war between Kelvin's, the Victorian times. There was a proxy war. Things were very gentle. There wasn't any Fox News or anything no Twitter to power raging infernos of argument. Instead, people would stand up and argue. And so there were proxy wars between the supporters of these guys and meanwhile, sciences of evolution, sciences of evolution-based biology and physical geology, both of which are needed to understand these two types of arguments, were evolving. People were going somewhere with it. The younger generations were taking off. And Kelvin and his dwindling number of supporters kept their heels dug in, and they were eventually left behind. So here's the thing. Kelvin, to us, is perhaps better known in the history of science as being a curmudgeon. In his later years, he tended to, disregard all of the new things that the young kids were working on. He never fully accepted Maxwell's theory of electromagnetism. He had reservations about the existence of atoms. He didn't believe in the importance of radioactivity. He famously argued that that flight using heavier than air aircraft was impossible based on his own equations of fluid mechanics. And he just kind of so he got this reputation of being sort of, what do you want to call it, a jerk. So but let's get back to what he did get right. Okay, one was the one question that Kelvin left unanswered and which remained to be answered in the 20th century was, what is the age of the universe? And how can we know? And the answer to this was that people found out that the universe is expanding, and from there they could estimate the age. And so the discovery in 1929 by Edwin Hubble, that first he realized that galaxies were outside of our own galaxy. These little galaxies were outside, they're farther away than the edge of our galaxy, our own Milky Way galaxy. Then he measured the distances to around 25 galaxies, and from there he measured their speed using the redshift of these receding galaxies. And from there he found that the velocity gets larger with distance, and deduced Hubble's law. He got the slope, which is Hubble's constant. Now, the slope gives you velocity divided by distance. And so you can rearrange that there's two equations in this talk. I'm sorry. I apologize. So slope is equal to velocity times distance, velocity divided by distance. And so if you multiply this out, you get distance equal to velocity times time. And from there, you can figure out, if you know how fast it's expanding, you know how much it's expanded, you can deduce how long it's been around. And from Hubble's constant, from a modern measurement of Hubble's constant, it took a long time to get it right. It may still be, there's still people arguing. It's now around 14 billion years old. That's the estimate you get from Hubble's constant. Today's best estimate, or at least when I made this slide, it was 13.79 plus or minus 0.037 billion years. So in other words, billions of years old. Now, so the Big Bang, the idea that the universe was created, that the universe began in some way and then evolved over time, is an idea that goes back to a lot of the inventors of the theory behind Hubble's law, but it was really captured and crystallized by George Gamow, an immigrant from Russia who came to the United States in the 20s. He was born 1904 in Odessa, which is now in Ukraine. He traveled. He invented the theory of tunneling in quantum mechanics. He realized that the process of tunneling was an important contribution to the fusion that powers the sun. So Gamow and von Weizsäcker discovered the theory that eventually Hans Bethe perfected. And for our story, it's important that he realized that it was possible for the elements, or at least some of the elements, to form during the Big Bang. And the famous paper by Alpha, Bethe, and Gamow. Okay, so it's by Gamow and his student Alpha, and they put Bethe's name on the paper for laughs. Okay, and he also, in addition to his early work on the creation of the elements in the Big Bang, he also predicted the cosmic microwave background would be evidence of the Big Bang. He predicted this in 1948. This is Alfred Gamow and Hermann. He did try to convince Hermann to change his name to Delta, but he didn't succeed. And but anyway, these are really the two most important pieces of evidence of the Big Bang as we know it. So the idea is, that in the first 15 minutes, the Big Bang made most of the visible matter in the universe. 73% hydrogen, 24% helium, and this is now accepted as true. In our current picture, after the Big Bang, there's a rapid inflationary stage in which the universe is really expanding under its own energy, being pushed apart, and then it goes into a stage of long-term expansion in which it becomes basically a plasma of quarks and gluons. Okay, I have to mention that at this point, this is the only part of my lecture that I actually know anything about, because this is my field of expertise, okay? From here to here. The rest of it is just like I read stuff, okay? So after the quark-gluon plasma phase, you produce neutrons and protons from quarks and gluons, and then this produces eventually all of the cosmic microwave background, and then eventually all of the matter, the galaxies, and Lord Kelvin, and all everything else that we see. Okay. So Gamow didn't have all the details of that right. Far from it, but he did have the general gist. And so we owe him a great debt of gratitude for that. Now, the expansion of the universe. So what's the evidence for the Big Bang? There's the expansion of the universe, first of all, which explains Hubble's law of the galaxies. The age of the universe comes from the oldest and most distant stars. The fact that the oldest and most distant stars are different in chemical composition and in many ways from the stars that are close to us. Those have to have formed much earlier than the stars that are close to us. In addition to that, that Big Bang creates the chemical elements, the alpha, beta, and gamma theory, and then the cosmic microwave background, which comes from alpha, gamma, and Herman, and the relic black body radiation, which has been discovered in the cosmic microwave background. So this is the idea of Gamow, and as he's proposing this idea, the universe is expanding. There was a Big Bang which made most of the visible matter. He's opposed by the great astronomer Fred Hoyle, and he says, well, basically, look, the universe isn't really expanding. It only looks like it's expanding. And the universe, the Big Bang didn't make all of the elements of the universe. It couldn't have. The fusion in stars is what makes all the energy in the universe, okay? So Fred Hoyle, probably you know about Fred Hoyle because he's one of the greatest astronomers of all, astrophysicists of all time, right? He's also knighted. Sir Fred Hoyle was born in Yorkshire, England. He did his most important work, path-breaking work, on the synthesis of elements in stars. His first work was in 1946. He'd probably done it earlier, but 1946 was the end of World War II, and people were now allowed to talk about nuclear stuff again. So a lot of these papers came out all of a sudden in 1946, and his was one of them. And the famous paper in which he talked about the fusion of all of the fusion, the production through fusion of all the elements, came out in 1957, and but along with this work, which is now really just the cornerstone of what we now understand as astrophysicists. There's the steady state theory, which opposed the Big Bang theory, and he kind of came up with that. And so he was had a named chair, a Plumian professor of astronomy and experimental philosophy in Cambridge University. He was knighted in 1972. He's a well-known radio personality. And he wrote science fiction books that people read. He was an extremely well-known guy. And he was also the guy who named the Big Bang Theory because he was making fun of it. And he said, well, it's pretty ridiculous to think there was just some Big Bang and all of a sudden all this stuff was here. So he came up with, the name of the Big Bang Theory. And so let me talk about here for a few minutes the origin of the chemical elements by alpha, beta, and gamma. What they did was they thought that all of the elements in the cosmos could be built up by taking smaller elements and adding neutrons to them one at a time. And you would just make one after the other. Hydrogen, deuterium, tritium, the isotopes of hydrogen, then helium, then you keep going. And they did a calculation in which they got this curve. So this is their theoretical calculation. And these are the measured abundances at the time. And what you see here, this is like I'm telling you, for a theorist, if you see this bunch of data and you have your curve, it goes right through the theory. You're like, wow, we've got it. This is it. We've got it. So his idea was that you could make all the elements in the Big Bang. And there is one small problem, and the problem is that there's no stable atomic nucleus of mass 5 or mass 8. So you can't go from 5 to 6, and then from 6 to 7, and then from 7 to 8, and then 8 to 9. So you can't build up the elements the way Gamow wanted to in the first 15 minutes, okay? The processes have to be much slower, and you just run out of time while the universe is small enough and hot enough to power all these nuclear reactions, okay? So stellar nucleosynthesis was Hoyle's discovery. He started with him. He realized that fusion and red giant stars could generate elements from carbon up to iron. And he realized that supernova explosions and other energetic processes, he didn't know about neutron star collisions, but neutron star collisions, which we recently heard about from LIGO, are also responsible for generating the heavier elements. And he used nuclear physics to calculate the rates of these various reactions. And this led to the famous paper by Burbage, Fowler, and Hoyle, in which they calculated the abundances and got them right. And the idea is that the explosion of stars, eventually in supernova, causes the elements to spread across the galaxy. And this is, really the cornerstone of the standard, you call it the standard model of astrophysics. And this is where, Carl Sagan told my generation that we were all made of star stuff. And it's just. So now here's a picture of the Burbages and Fowler and Hoyle standing in front of a train. Fowler was a big fan of trains. And so they realized that stars built the elements heavier than lithium in the right cosmic proportions. But there was a problem with their idea too, which is that in the sun and in other stars, there's too much energy around to really make the light elements. Basically, you burn deuterium to make helium. You don't have enough of the light elements in order to explain the cosmic abundances that astronomers find when they look out into the cosmos. So their theory explains only part of the elements. It explains most of the stuff we're made out of, but it doesn't explain most of the stuff in the cosmos. So in the end, Gamow realized that he should concede defeat, and he did so being a man of wit. He came up with sort of a funny joke in which he said, in which he said that in the beginning God created radiation, and it's a form of Genesis, and he said, "Let there be mass 1, let there be mass 2," and then God saw it was good. And then God continued to make all of the elements, and he made all the elements up to the transuranium elements. But then he looked back on his work and found that it was no good. In the excitement of his counting, he missed calling for mass 5, and so naturally, no heavier elements could possibly been formed. And then he was so upset by his mistake. God said, "Let there be Hoyle." And then there was Hoyle, and God looked at Hoyle and told him to make the heavier elements any way he wanted to. So this is Gamow, and this is really what a gentleman scientist does. Eventually you realize the evidence just doesn't support you all the way. I got something, I didn't get everything. Have to admit what's going on. But then there's Hoyle in the steady state universe, right? So Bondi, Gould, and Hoyle came up with an alternative to the Big Bang, and it started out with them seeing a horror movie. Jeez, I just saw them. You know, if you ever watch Turner Classic Movies, they show this routinely on Turner Classic Movies. It's an old horror movie from like 1948, right? And the three of these guys were working together, and they went to the movie and they saw it, and it was a horror movie in which there were 5 vignettes of terrible, horrible things happening to people, and then in the end, this guy realizes it was all a dream, and it goes back to the beginning and goes around in circles over and over again. And Hoyle comes out of this movie and he says, what if the universe is like that? What if the universe is, well, it's not a horror story, but it goes, depends on how you look at it, but it goes around and around forever and ever, and it never ends perpetually. And so they went back to work, and they came up with this idea that the universe could be eternal, infinite, and unchanging. The idea is that there's got to be steady production of new matter in the space between galaxies, and that the steady production just makes it seem as if the universe is expanding. Okay? This is the idea. And so he had to tune the amount of production of matter in order to explain the seeming expansion. And this would explain Hubble's law of galaxies. And he also had, at the same time, his theory that all the elements are made in the stars. And it does explain almost all the elements. It just doesn't explain hydrogen, helium, and lithium. And but his theory would not in any way give rise to a cosmic microwave background radiation. And according to him, the distant galaxies would have to be the same as the nearby galaxies, because everything's eternal. So the stuff that we're seeing that's far away, even though it's billions of years older than the stuff we're seeing close, is the same stuff. It's just that he's only seeing as far out as, things are just basically infinitely far away. Okay? So then Hoyle, people did begin to discover that the distant galaxies are different from the nearby galaxies. But also at the same time, they discovered the cosmic microwave background radiation, Penzias and Wilson. They were trying to communicate with satellites and discovered a hiss from the radiation of the background from the Big Bang that's the same in every direction that you look and very uniform. And they realized that this, after very careful work, they realized it wasn't that their radio receiver was broken. It was that there had to be radiation, and that the only explanation of this was the Big Bang. And so here's another picture that was made by Gamov, in which Gamov is shown here emerging from Lem is the stuff that he called the matter that the early universe was made out of. He didn't know about quark gluon plasma, so he came up with a far cuter and funnier name, Lem. And here is the here's Alpha and Herman, and their idea came out of his crazy dreams, and the cosmic radiation that they predicted, lo and behold, was discovered. So how did it go with the evolving versus the steady state universe? There were 50 years of argument over the age of the universe. In the meantime, both astronomy and nuclear physics advanced rapidly. And for most the discovery of the cosmic microwave background killed Hoyle's steady state model. But Hoyle and a dwindling number of supporters, eventually all of them giving up one after the other, except Hoyle, kind of hung on to this idea for the rest of his life, as far as anybody knows. So what was Hoyle's motivation? This is interesting. In a BBC interview, he said the reason scientists like the Big Bang is because they're overshadowed by the book of Genesis. It's deep within the psyche of most scientists to believe the first page of Genesis. In other words, the Big Bang seemed to him to be a creation event. Hoyle was an atheist, and he felt that religion and religious thinking had no place in science. And so he just had a gut reaction, and he hated the Big Bang. Okay, and this is why he stuck with the steady state for so long, because it was an idea that had no beginning or end, and with new matter constantly forming. Okay, now who did like the Big Bang theory? It turns out that from very early on, the Catholic Church supported research in Big Bang cosmology, and this is, they realized eventually that they got it wrong with Galileo, and they didn't want to be in that situation. They didn't want to be that guy again, So they decided to wise up and have educated people around them and listen to them. And they had scientifically educated people around them. And so Lemaitre was himself an abbot in an abbey. That's what one is when one lives in an abbey, right? He was a man of the cloth, what I mean to say. He was the guy who first came up with the idea of the expanding universe, that relativity predicted the expanding universe. And so there were people, so the church was very much behind the idea of a Big Bang. And the reason why was because they really liked the idea that the universe didn't exist before a time, and then after a time, it sprung into existence. Okay, because that does, so they do like it. And but for me, the only pope is Neil deGrasse Science, who says the good thing about science is that it's true whether or not you believe in it. And I think I'll end with that. Thank you. Mm-hmm. Where is my timer? I've gone enormously over, have I not?
That's quite all right with us, Sean.
I'm sorry.
No, don't be sorry.
You're fine. It's a great talk.
Thank you.
Okay. We're going to go ahead and take questions. We've lately just been letting people chime in and do it, and that seems to have worked so far. So we'll try that and hope it stays under control. We will have to have you stop screen sharing though, Sean, so we can see more pictures there.
Sure.
For people. Thank you.
Sorry about that.
Okay, questions. Richard, yep. Go ahead, Richard. Didn't you raise your hand there?
Oh, you're muted? Are you No.
There we go.
Oh, thanks.
Okay.
Who's the bigger curmudgeon, Lord Kelvin or Fritz Zwicky?
Zwicky, I don't know. I mean, he was kind of my impression is that he was just a troublesome guy. I don't know if he was kind of a visionary, right? I mean, he came up with dark matter and all that stuff.
Neutron stars. Yeah.
Neutron stars. I mean, he's like a visionary, but he's just hard to get along with, you know. And,
if people don't know, he called all of his enemies spherical bastards because no matter how you look at them, they're a bastard.
So it's true that his daughter is carrying on the Zwicky family name in another of the clubs I'm in, which shall not be named. She actually is feuding with one of the lifetime club members, Ken Burton, and initially wanted her rebuttal written in that newsletter. She since sent an email saying, please don't post my rebuttal. We've taken the matter up ourselves. So I wrote the response saying the board has received your request and will not put it in the upcoming newsletter. So yeah, I can vouch for the whole Zwicky family. They're still who they are.
Cool.
It's good. I mean, it's good, but maybe they move your office to the basement. I think.
I just
Go, John.
I just wanted to add that when I was in high school, I was introduced to Herman Bondi through his book, The Relativity and Common Sense, which is still, I think, one of the best introductions to relativity for non-physicists. But we became acquainted with Bondi, and of course he was a strong advocate of the steady state cosmology. All this stuff kind of quietly evolved during my lifetime, and I missed most of it until I got interested in astronomy again in my old age.
It's fascinating. Yeah, there are a lot of people who still know Hoyle, and I didn't mean to make him seem like he was a bad guy in any sense, right? Because he's really, in fact, a path-breaking individual, right? He came up with a lot of really powerful and important ideas, and it's just Gamow, yeah. Gamow also wrote a bunch of popular books, but they didn't knight him. So I think Hoyle was doing better in terms of, the royalty.
Doug Warshow has chatted a question. Does your work on quark soup add any details on the early universe?
It does. It does. Not as much as we originally hoped. I mean, it's part of the picture of the theoretical consistency of how stuff happened. It's also part of the description of what's going on. So when people talk about the formation of dark matter and the evolution of dark energy, quark matter is in their equations. Basically, my work has had more to do with experiments that are taking place at the CERN Large Hadron Collider and at the Relativistic Heavy Ion Collider in Long Island, where they're they collide nuclei at very high energies and produce quark gluon plasma, and the stuff goes splat and flies apart. And it's the splitter splatting of this, the application that allows us to apply fluid mechanics to these collisions and figure out what the properties of quark matter is. It turns out it has the lowest viscosity of anything that we've encountered. Viscosity. But, that has something to do with the early universe, but it doesn't really have very much to do with the generation of the elements or any of the big things.
Looking for more questions?
So I actually work with Claude Pruneau. I don't know if he's here today, but he's one of your members.
Yeah, he joined the club a while back. We had him present. It's been 3 times now, I think, to us.
Yeah, he's great.
Yeah.
Claude was actually logged into the YouTube early on. I don't know if he hung on or not. We don't get IDs on there, but he did give a smiley face and said hi. So
Cool.
Yeah.
So any other questions for Sean? We're not usually this quiet.
I think one of the things here is that this was such an interesting, broad survey of so many topics. It really covered an awful lot of ground. I think a lot of us are going to think about this and then come up with our questions. Unfortunately, sometime later.
Well, what I can do is in the chat, I'll put my email address. And you can write to me. And I will reply. Okay, there it is. I mean, most of this stuff came about because what we wanted to do was come up with a way of illustrating the scientific method to students who are not necessarily science majors even, like high school teachers, but not necessarily science majors. Like they could be history majors or special ed majors, whatever they're going to do. There would be, but educators, right? And so the idea was to try and find a way to explain to them, just how science works and how scientists are just people. This is a pretty good example of how scientists are just people, I would say. And the scientific method may work over the large scale and over the long times, but individuals can get stuck and waste their time and energies. So the idea was to make a whole course out of various different explanations like this. And this seemed like it would be a great idea, but then somebody else wrote a book. It's called Brilliant Blunders. Give me a second. I have to cite him because Mario Livio.
Yeah.
And so he has lots of other stories in there. He talks about Kelvin, and he might also talk about Hoyle in there. But I was smart but not smart enough, right? So this other guy wrote a book, and I got to talk at it.
Well, the history of science is very interesting. Reading history of science books from the past, and even reading an astronomy, a college astronomy text from the 60s. I recently looked over my late wife's introductory astronomy text, and it's really interesting. And of course, many historians criticize history as being a set of lies that everyone agrees on. And the history of science, we have to look at it charitably, because we're so damn smart. And we have to think of the culture within which people worked, the pressures under which they worked. It's always nice to have a job, and sometimes you have to agree with the big guy in order to do that. And then just things like you mentioned that Hoyle was not knighted. There were a couple of wars in there, and there were an awful lot of soldiers that got knighted, and I think some scientists got skipped over. some other people in the realm of thought. So there are a lot of things that happen in science that are not scientific.
Yes.
We have a question from Thomas Morris. He said, did Hoyle claim that nuclear fusion in stars explains the redshift?
I don't know. I think the redshift had to come from the generation of matter in between the stars. Although I'm not sure. It's one of those things that it's hard to learn a wrong theory. But although it's not wrong in its elements, it's wrong in just the overall fact of it, because there's no generation of new matter. I mean, but energy is conserved, as far as we know. But the redshift somehow comes from. Yeah, I'm not sure. I'm not really sure.
The other question we have geared up is from Doug Warshaw, and it says, do quark stars have different nuclear synthesis progression?
Quark stars. Now, quark stars are like neutron stars, except more. And what they have is, so inside the star, there's a possibility. We don't know if they exist, but there's a possibility that as the neutron star, as the star is collapsing, the compression forces electrons to combine with protons to make neutrons, and this brings neutron-rich matter. But now, if the star is massive enough, it'll keep on compressing, and it will break the neutrons, which are each made of 3 quarks, into a sea of quarks. Now, how that happens is the not only do you have the usual up and down quarks, but you also have strange quarks. And the strange quarks that are present allow the thing to compress further, become more compact, and to spin faster. So, yeah, talk about a whole bunch of ideas, but these things they're like neutron stars, except they would spin faster, they would have faster periods, and they would be smaller, and their whole structure would be different because they can't really have the same kind of crust that neutron stars have. So the quakes and various different phenomena that astronomers study would not be the same. And so every once in a while, somebody thinks they find a candidate, and they get very excited. The candidates, we're just waiting till somebody finds one, and then we'll be in business. I'll have a whole new job.
We do have a couple of comments here. One is from member Steve Howie, who I wanted to point out that he does not have internet in his area, so he's having to watch this on his phone. But his house is a signal blocker, so he's sitting in his garage with his phone on a tripod. We really like your resolve, Steve, and that just shows Lowbrows will do anything to attend one of our meetings, huh? Also from Krishna, he wanted to point out there's a short history of nearly everything by Bill Bryson. It's a great read and covers much of what Sean discussed today, focused on the process and personalities behind science.
Sounds good.
With that, any last-minute questions for Sean? Okay, I'm not seeing any. So we really appreciate it, Professor Gavin. Can we get a big hand for him? Thank you very much.
Thanks. Thanks
So
a lot.
one other little detail, we like to, as a small token of our appreciation, give our guest speakers either a club t-shirt. This is actually a sweatshirt, but it looks like this. Or you could have your choice of a club hat, baseball style. We have two different types. One is more what you'd see as a traditional type hat, you know, higher profile. It has a stretch type fit in it. Comes in a small, medium, or a large. And then we have another type, which you'll see is kind of a lower profile. It's floppy and has an adjustable band on the back, so it's like a one-size-fits-all. So do you have a preference?
I think I would like the t-shirt.
Cool. What size?
I mean, large.
Okay. If you could just send me your shipping address,
Sure.
and I'll get it to Doug. Or you can send it to Lowbrow Doug at, I don't know, you want to give him the address, Doug?
Yeah, I'm the guy to send it to, so if you want to send it to lowbrowdoug@gmail.com, your address, and I will get that out to you shortly.
Okay. Thank you very
And
much.
Thank you.
And I have your email too, so.
Okay. So that brings us to officer reports. I am very short because I have nothing to report. Do you have anything for us, Joy? Cool. Thank you for doing the minutes. How about Jim?
This month, I've absolutely nothing to impart. So
That was quick.
yeah.
How about Adrian?
Nothing to report lowbrow wise. Still doing a lot of travel to get images, and also became the treasurer of WAS. So Doug Scoble, I may be hitting you up for some advice on handling a treasurer duty thing. But as far as VP lowbrows, nothing to report. As far as the GLAC connection, which may as well be a part of it since most of us are helping with GLAC, there's still discussion of whether we're going to do a hybrid event or go back with a fully virtual event. Given the University of Michigan stance and that no activity through June, that will factor into the decision as we watch how the vaccination of the COVID vaccination goes. But we're looking to be safe as opposed to
eager,
just moving forward and declaring that we're going to do something hybrid and figure that out. So,
Adrian, to add to that, the DNR still is limiting events on their premises to 25 people outdoor with precautions.
okay, so that's and we're following that too for sure. So, I've got a weird light in my eye, but that's too bad. So, other than that, yeah, we're watching and waiting. The GLAC board really didn't change. It's the same board as last year. So I got stuck doing president. I tried to get Jeff Koopmanis to take over, but he refused.
Not a chance.
So as always, if you have questions about GLAC, you can ask me. And since I'm infiltrating WAS, you all are always welcome to go to one of their 2 meetings as well and see how it is. But that's all I've got.
Thank you, Adrian. I thought I saw Dave Jorgensen earlier. Is he still with us? I don't see him, but and maybe I'm mistaken, but I thought I saw him early on. And I don't hear him chiming in, so I'm going to assume he has left.
I don't see him in the
or
list.
I hallucinated. How about Doug?
Doug is here. Can you hear me?
Yes.
We can.
Yeah. Yep.
Okay, good.
We hear you.
I'm sorry? Someone said something. Anyway, we have a balance of $9,745.40 in the Treasury. We're up to 162 memberships. One new member, Stephen Howie. I see him on there. I think he's the guy that was in his garage because he wasn't getting good phone service or whatever.
Oh, that's right. I didn't put the
Yes.
name together. Yeah, that was him.
Yeah.
Welcome,
him.
Stephen.
Yeah.
And as far as not a lot of activity, mailed a shirt to Pat Seitzer for his talk last month. Sent Don Foey some money for the newsletter printing and mailing. And of course, our monthly AT&T messaging bill, which is $15.85 every month. So for our hotline for open houses that we just never have. So, but I think we need to keep that going. But that's all I have to report.
Thank you, Doug. Jack.
Yes. And as we're doing for the, can you hear me?
Yes.
Yes.
Okay. Observatory, building and that are fine. We're still waiting for some more discussion on the internet. And the other thing coming up was that 300-foot tower that they're building over there off Stinchfield Road. That some more information on that comes up on the 22nd. Dexter Township has some kind of meeting on that day with some more information about it. But other than that, like I said, building and interior is fine. So with that, I'm just going to turn it back over to Charlie. And if you could see my photograph, you can see that picture of the observatory open. And we get hopefully maybe sometime around August or September, we may actually be doing that again. So we'll see what happens with everything going on. Other than that, that's all I've got for the observatory.
Thank you, Jack. So when were you up there last?
Oh, 10 days ago or so.
Okay.
There wasn't that much snow there. There is more snow now. I mean, it's because what's happened last week.
Yeah, that's what I wondered if you were up there
And
since we got the last snowfalls.
No, not the last couple of days. I haven't
Okay.
been up there. Other than that,
You know, when there's this much snow on the ground, it gets to be a long walk to the observatory.
Yeah.
yeah,
I had
that's very true.
somebody call me yesterday that's a U of M LS&A student that wants to go up there, have somebody let him in so he can take pictures of the place for some project he's working on. So I wouldn't have to disappoint him tomorrow, but that's one of the reasons I asked about the snow. So
Yeah.
You can always send we've got plenty of pictures we've already taken. I guess we could send a couple.
Actually, we
yeah,
got
I guess
those.
I don't know the.
I say we got those pictures we did when Jack and I were out there with the ITS people, and those are from this past fall.
Mm-hmm.
Yeah.
So
yeah, I'm going to call him tomorrow and I'll see what he has in mind exactly, if we can really
Yeah.
help him or not. But I know I'm not planning to drive up there to let him in and
No.
well, shoot him my
hang
way
around
out.
for whatever period of time. So
Shoot him my
and then he
address.
said
I'll
that
give
he
him
might
pictures.
consider joining the club later, but I think that was sort of a little perk to try to get me to say yes. But I don't know.
You really
Okay.
don't want to go up there unless you've got an all-wheel drive vehicle.
Exactly.
Or
Yeah.
four-wheel, whatever, something like that right
Yeah.
now.
Yeah. That's
Once
just
the
one of the
snow
reasons
melts
I want
down.
to say no.
Yeah.
Just shoot him my email address. I've got recent pictures with no snow and some inside pictures as well. So
Okay. Yeah. If he thinks that'll help, I'll do that. So,
Yeah.
Thank you, Jeff.
I'll be glad to share them
More
with him.
recent than mine.
Okay. How about Don?
Hi. My request last month for newsletter articles was responded to very well by the membership, and several people sent me some very nice articles. So I have some nice material for next month's newsletter. I still haven't heard from anybody willing to become the new newsletter editor. And I've taken on a project where I'm creating an index for the 4 years of newsletters that I produced. So they'll have an index. I'm going to try and make it a robust index by author, by subject, by photograph, and see how many ways I can index the issues. So I'm working on that project, and hopefully we'll have that done by after the April issue, and I'll integrate that into our website. And I'll work with Dave Snyder or Krishna or Jeff or something to work on getting the index integrated with our other indexes. That's all I have.
And if we don't have somebody that's willing to be newsletter editor, we might have to draft somebody. So you can consider that a threat, everybody.
Dope.
Well, it's like I said, my last plea there is if we don't find somebody pretty soon, we won't have a newsletter. And that's, that would be sad. So we'll keep working on it.
Well, all the faces that we see right now are probably in consideration.
Well, I was going to say, are present officers exempt from draft, or?
Yes.
Yeah. Okay.
Did you see how many people just shut off their video camera screen?
Yeah, they're running like hell.
I just want to add that I do the newsletter for the Kalamazoo Club. The next newsletter, the March issue, will be number 260 for me.
Ooh.
Oh,
And they each take about at minimum 6 hours to do. So do the math.
Yeah.
I started doing it in 1996. I got a 4-year break in the early 2000s, and I've been doing it ever since.
Very commendable.
Your compadre in the was is Dale Timmy, and I'm not sure how long he's been doing it, but
you're a better man than I am.
I think he's been doing it for a while too.
Yeah,
it's an undertaking, that's for sure.
You know, there's folks that are especially suited to particular things, and they do them well, and are happy to keep doing them. But the club as a whole has to step up and take on some of these things. You know, yeah, it's great, Richard, that you wanted to do 260 issues of your club's newsletter, but the club itself has to do, you know, the membership has to spread out some of these tasks. And, you know, we always, you know, this is something that's been a concern since I've been in the Lowbrows, is that the membership has gotten pretty gray. You know, right now we've got a nice mix of older and younger officers, but that hasn't always been true. And we've had to work to have the mix that we do now. And the only way that happens is if people step aside and say, you know, I'm done, and the rest of you have to pick up the, you know, the slack. There's some things that we're stuck with, like people, you know, only so many of us can have a key to Peach Mountain under pretty demanding, under demands of the university that we can't do anything about. But other than that, you know, we can spread this stuff out with, you know, because we've got 160 members. I mean, there's no reason we can't have somebody doing the newsletter that hasn't done it before. You know, I did it before Don. I did it for 5 years. Mark, the press, did it for 5 years before that, and that was his second tour. You know, now we're going back almost 20 years, and we've had, you know, 4 people do it, and that's fine, but it has to be somebody new. And, you know, and that's going to come along with some of these other jobs too, as time goes by. You know, Doug's been treasurer for a long time, and I hope he keeps doing it because he does it so well. The same with Charlie, but at a certain point, other people have to step up.
Yeah.
I will send a newsletter or an email out, encouraging people to volunteer as newsletter.
Yeah, put it on the front of the newsletter.
Okay.
Yeah.
Good idea.
Yeah, like a wanted bulletin or something. Huh?
Good idea. I'll make that in the next issue.
Yeah.
I'll put an email out extorting the virtues of being the newsletter editor.
Extorting the virtues, okay.
If you enjoy this newsletter, we are looking for an editor.
Yes. Okay, Jeff.
Tonight we had 37 max on Zoom and 6 on YouTube. I also going to just read what Krishna left for. It says, my report as webmaster. Have some uploads and maintenance to catch up on. The speaker schedule, I talked to him earlier before everybody got on, but the speaker schedule will be posted in addition to our calendar as a quick way to scan for just those events. So our 2021 calendar should be on the web when he gets a chance to get that up there. Other than that, I don't have a whole lot extra to add, other than I've been playing with computer software and other junk, as you all have seen. So
thank you once again for continuing to make sure our stream goes to YouTube. For those that missed the live stream or want to review it again while they're doing the minutes, Joy, it helps them out tremendously in getting everything accurate. So thank you for that. And we'll thank Joy again because she does most of the minutes for us. So give both a round of applause.
She leaves a real hard act to follow, which is a problem in a way.
Yeah.
So.
Yeah, it's been instrumental in the online meetings. And I'll also call out Dr. Brian Autumn hiding out there, who's done a couple of, for our outreach reports, he's pretty much done them, has some successful tours of the night sky through his observatory, and in particular touring Orion. Those were some very good shows.
They were.
Thank you, Brian, for doing those for us.
Much appreciated.
For all of us in astronomy, not just the lowbrows.
I did want to add, actually, I recorded Krishna's COVID briefing separately from the YouTube thing. It is in the YouTube, but I basically going to have an excerpt that we can post separately for just the COVID thing, since it's sort of relevant to the lowbrows.
Bad idea.
Yeah. It's sitting on disk someplace.
One suggestion that I have, we've been recording these meetings, for the last year or so, not quite a year, but eventually thinking about like the indexes for the newsletter, we probably should have a document somewhere on our website which lists the YouTube URLs for each of our meetings. So people can look with a summary of what the speaker was and what the topic was, so that people can go back, reference, and know to go.
To answer that question, Don, right now you can go into YouTube, and if you search for Lowbrow, you'll see a bunch of these. Now, I'm trying to figure. They are all in a playlist that I maintain, so all of them go into a Lowbrow meetings playlist. But I'm not sure how to publicize that. So it's like as a single point of entry. So if you go here, you'll find all the meetings. They're all in order. But generally, if you just search for Lowbrow in the YouTube searcher, it will find most of the videos there. So as a quick way to get to something, they're not necessarily in order. They're very weirdly ordered. I don't know what the scheme is there, but if you find one, you'll generally find the rest of them soon enough.
Well, that's good.
Yeah, that would be an interesting project, Don, to just take those and have them listed in the website, in addition to just searching. Now, we pick up new people by searching Lowbrow.
If you look
they learn about us through those.
When Krishna gets the speaker schedule on there, The speaker schedule's got all of the YouTube URLs in it, so perhaps we have, the past speaker schedules there, and they could be online just as easily. It's just a spreadsheet at this point, so.
Yeah, I didn't realize that either. Very good.
I can double check, but I'll make sure that you're on the share list for that spreadsheet, and you can publish anything you want anywhere. It doesn't matter to me. But if it's in PDF, it'll be easy to click on that way. So let's check on that while I'm thinking about it.
So did I miss the intro? I know, Richard Bell, you come to us from Kalamazoo. Did I miss the sort of intro about your club and just like the brief overview of how you guys are doing things?
I didn't really give a brief overview, but I could.
I say we just a real quick overview. Having a visiting club, I think it's a pretty cool thing. I wouldn't mind hearing a little bit about the Kalamazoo Club.
Yeah, I'll just start from the beginning. The Kalamazoo Astronomical Society was founded in 1936. We are the oldest club in the state. Probably one of the largest, if not the largest right now. We have, I haven't tallied it up recently because I'm still waiting to get rid of either have the people they haven't renewed yet to renew or drop them off the list. But I'm pretty sure we are about, if we have not done it already, we're going to very soon hit 200 memberships for the first time in our history.
Nice.
At the end of last year, we reached a record of 191, but the 5-part lecture series that we're doing right now has brought in a lot of people from out of state. We picked up a lot of members from all across the country, which I don't know how long we're going to keep them, but it's pretty cool. Especially if we can keep doing the Zoom thing, or at least recording the meetings and putting them on YouTube or something like that. So yeah, we have a great deal of members. We meet on the first Friday. I was going to mention you're all welcome to join us for our next meeting on March 5th at 7:00 p.m. It'll be on Zoom. You can register through our website. We have Dr. Pascal Lee from I think like the Mars Institute, but he's also from the SETI Institute, and he's given a talk called N is approximately equal to 1, the search for life in the Milky Way, or something along that line. And so we're really looking forward to that talk. But of course, tomorrow we have part 3 of the Introduction to Amateur Astronomy lecture series. We currently have over 850 people all over the world that have registered, and about half of those actually turn up on Zoom. The rest may kind of wait to watch it on YouTube, I guess. But so far, it's been pretty good. And so that's tomorrow at 1:00. You have to register, but if you don't really want to, you can probably find it on our YouTube channel, because we will do a live webcast on YouTube as well, in case we hit the 500 limit on the Zoom webinar thing. People will have to go over to the YouTube channel, but some prefer to watch it on YouTube anyway. And the topic this time is called Binocular Basics. So guess what the topic is about? And the day after the general meeting on March 5th, March 6th, we'll be doing the one on telescopes. And I really get into the nitty gritty of telescopes. And then we end up on March 20th with astrophotography, where I mainly just cover the basics, starting with tripod photography. I try not to get too techie since it's mostly beginners. But also, we have a 12x12 roll-off roof observatory at the Kalamazoo Nature Center. As I mentioned early on, we just put a 16-inch telescope in there, a 16-inch Meade on an Astrophysics 1600 mount. And that is not even our flagship telescope. Our flagship telescope is the remote telescope at Arizona Sky Village. We have a 20-inch plane wave with a 4-inch Takahashi on a Paramount ME2. And that's now seeing regular use by members. It took us a while to get the bugs worked out, but it's working fabulous now. So that's kind of the KAS in a nutshell.
Yeah, you got deeper pockets than we do, that's for sure.
We raised $122,000, and 60% of that was from members. Wow. Pretty much the entire local observatory, we call it Owl Observatory I don't know if anyone remembers, it's been some time. Long time ago in the early 90s, there was a 3-part series in Astronomy magazine called How to Build Now Observatory. So we just kind of kept the name because it's at the Kalamazoo Nature Center and it kind of goes along with the theme. Although many Nature Center people think, hey, where's this observatory we go to watch owls at? So they get confused. Yeah, we were supposed to have the dedication for the new observatory telescope here in town on March 30th last year. It was a gorgeous day, but of course we had to cancel. And we're going to try to have it again maybe at the end of March this year, or May this year. But you know, who knows?
Thank you, Richard.
And you're always welcome to check our website too. It's a pretty damn good website, if I do say so myself, since I do that too. I just won the Great Lakes region of the Astronomical League Award for our website. So it is a award-winning website. I can say that now.
What's the URL, Kat?
kasonline.org.
Is that HTTPS?
Yes.
kasonline.org.
Yep.
Good. Typable.
Back in the early 90s, I wanted to get kas.org, but they shot me down, and now that belongs to the Korean Astronomical Society. Damn it!
Okay, thanks again, Richard.
You're very welcome.
Welcome. Glad you could join us tonight.
Yeah, that's great.
And hopefully, some of us will join you.
Yeah, absolutely.
So, cool. Does anybody have anything else? Okay, I don't hear anything. Do I hear a motion to adjourn? Brian?
I cleared this with Jeff. If anybody wants to stick around, if they're still awake, I can share my screen and we could just do by suggestions, anything we want to look at through my telescope, because I'm up and running with the remote scope right now.
Excellent.
Oh. Well,
Okay.
I'll stay online for that.
All right.
And we can do it as verbal, because with the YouTube, remember, it was only chatting, right? You know, typing. So at least this allows us to talk about what we want to see.
Right.
Observating works for me.
Yeah. Did I see John make a motion to adjourn? All right. Support? Anybody opposed? Okay. Looks like we're adjourned at 10:07. Thank you, everybody. And I know I'm going to stick around and enjoy Brian's show here. So
I am going to stop the YouTube stream, though.